And all the participants, I welcome you all to this last lecture in this special DLP program on remote sensing and GIS applications for agriculture. So the today's lecture assigned to me is basically the overview of RS and GIS applications, especially for soil resource management. Myself, Justin George, I'm working as a faculty in Agriculture and Soils Department at Indian Institute of Remote Sensing. So during the past 4 days, my esteemed colleagues, they might have delivered different lectures related to the remote sensing, the basics. So from that, everyone will be knowing that remote sensing is basically the visual as well as the digital interpretation of various remote sensing data products. It may be either air photos, digital, or the reference data, ultimately converting them into various information products, including various maps, their statistics, as well as various GIS data sets for a large variety of users at various user groups, as well as the various decision makers. Basically, the users as well as the various decision makers are our target audience. So apart from the normal multispectral, hyperspectral, and microwave data, the colleagues have delivered during the past 4 days, there is another type of remote sensing derived data, which is basically comes under the group which is known as the digital elevation data. So you might be hearing the terms like DEM, DSM, as well as the DTM, which are basically different forms of digital elevation data. The DEM, it is generic term for any digital representation of a topographic surface. And the DTM and DSM are basically the derivatives of DEM data only, where the terrain model, it indicates the bare earth height, whereas the surface model includes the height of buildings as well as trees. So there are n number of data sources based on which the different digital elevation models are generated. The different data sources include the ground surveys, airborne photogrammetric data capture, existing cartographic surveys, topo sheets, airborne laser scanning, the stereoscopic or radar-based satellite image. So through different types of remote sensing, the digital elevation data can be generated and used for various applications. And this digital elevation data, it has got a widespread use widely with respect to agriculture and soils, mainly in case of watershed management, soil erosion modeling, as well as various digital soil mapping approaches. So these images clearly show the difference between surface model as well as the terrain model. Here you can see it is the surface is mainly devoid of all the structures. This is basically the terrain model. Here the height of the trees and other buildings, all these structures are also included. So coming to the terrain analysis, it is basically a term which is used for the various techniques which many users are employing for derivation of terrain parameters from DEM as well as their application of various terrain parameters. So it mainly includes the general task including DTM as well as DEM generation, the manipulation, the interpretation, the visualization, as well as the application of these different things. The digital terrain modeling or analysis, it has widely replaced the qualitative as well as the nominal characterization of topography. That's why people have been increasingly using this for the past few years. It also enables to derive any other terrain attributes quantitatively, especially like slope. Similarly, it also gives the quantitative measurement of elevation, also helps in the visualization of three-dimensional 3D models as well as the digital storage and manipulation of digital data. This table shows the various characteristics of different DEM generation methods like the ground survey, the stereoscopic imagery, the laser scanning, as well as the radar interferometry with respect to their accuracy as well as the cost. So depending on the purpose or the funds available or your particular task you are aiming, you should choose the different types of DEM generation methods. So with this background, coming to the why remote sensing has widely been used for agriculture as well as soil studies, mainly because of these different characteristics. Ultimately, it provides us with a very global coverage. It gives a periodic repeativity and gives high precision as well as accuracy. It's a very reliable technique. It's cost effective when we go for a regional or a country level or a big scale studies. It is eco-friendly also. Once the satellite is in the orbit, the operation and other things doesn't require any fuel or other things. Ultimately, because of all these things, it has been widely used for agriculture and soil studies, which are aimed at the sustainable development of the society. So when we summarize the various remote sensing applications for agriculture, these are the different aspects in which remote sensing, these are, it's not limited to only this, but these are the major applications of remote sensing in agriculture. It mainly includes the land use land cover mapping. My colleagues might have explained and described in detail all these things, the crop identification as well as the acreage estimation, the identification of planting and harvesting dates. So apart from this, I will be mainly focusing today's lecture on these four, which are highlighted in this red color, which is basically directly related to the performance or the estimation of various aspects of soil as well as the and their impact on agriculture. So the first and foremost thing, application of remote sensing with respect to soil is nothing but the land degradation mapping as well as monitoring. Then comes the soil mapping and monitoring. Then comes the watershed management as well as the soil moisture estimation. So coming to the land degradation mapping or monitoring. So in order to use remote sensing for sorry, land degradation mapping or assessment, first we need to know what is meant by land degradation. So as per the Glasgow estimation, that is the global assessment of soil degradation, it has distinguished the different types of soil degradation. The first and foremost and the most prominent type of land degradation occurring throughout the world, as well as especially with respect to our country, India, is nothing but the water erosion. It is nothing but the loss of topsoil by the effect of water, whether it is rainfall or as the severe runoff. Then the second is the wind erosion, which is more or less the uniform displacement of soil, mainly by the activity of wind. And it mainly occurs in case of arid, semi-arid as well as the subhumid regions, where the rainfall is less and the temperature is high. The third category is the chemical degradation, which mainly indicates the changes in the adverse changes in the chemical properties of soil. It mainly includes the various processes like acidification, salinization, alkalinization, laterization, as well as podsolization. Then comes the physical degradation. The physical degradation mainly includes the variations or the adverse changes in the physical characteristics of the soil or a particular piece of land, which is mainly the changes in the bulk density, the porosity, the permeability, infiltration capacity, as well as the structural stability. Then there is the final categories called the biological degradation, which mainly indicates the loss of organic matter from the soils, mainly due to mineralization, which is accelerated due to various intercultural operations as well as the various human-induced activities. So coming to the assessment of land degradation, the methods to assess the current land degradation, it mainly depends on the type of land degradation, whether it is physical, chemical, or biological, as we have briefly described. And mainly it's a very complex process having a lot amount of components. So that's why the assessment of land degradation, it mainly necessitates the assessment of each of these different component processes. Because acidification, the acidification may happen due to different types of causes. So all these things prove their importance with respect to land degradation, because it is a complex of various processes occurring at the same time. And coming to the major approaches currently adopted at various parts of the world for land degradation assessment is, the first and foremost one is the direct field observations using diagnostic criteria or simple visual indices, but it has got a subjective nature. But it's not possible to do a direct field observation at every region. It has got its own limitations with respect to accessibility, the cost, the time, and the area we can cover in a short period of time. And all these are some of the limitations. Then there is another aspect, which is basically the landscape units assessment, mainly the land systems and facets, where the uniform land units, they will be identified and they will be rated mainly based on various subjective criteria for identifying their potential or their limitations. Then the another methods many people have been using is nothing but the parametric semi-quantitative method, where the various indices will be computed, which will represent the various factors of land degradation. And there is another thing which is known as the rating system and the decision trees, where the computer automation will be, we will be putting a set of rules, and the images will be classified into different land degradation types, mainly by the computer automation. And ultimately, when we want to study the land degradation, which is a very complex process in totality, it mainly works with the simulation modeling of the various complex processes, where each and every component of the complex process of degradation will be studied in detail, and their synergy will also be studied. Coming to the role of remote sensing in monitoring and soil as well as the land degradation process, the remote sensing helps in monitoring as well as assessing land degradation, mainly by studying certain indicators which can be assessed as well as monitored. The various indicators of soil degradation, which can be easily identified or monitored using remote sensing processes. First one is increase in the albedo, the soil salinization, which can be observed, the water as well as the wind erosion, the soil moisture we can measure using various approaches. Then the reduced organic matter levels can be mapped. Then the soil structure deterioration as well as crusting, the changes in iron oxide contents, the sand activity as well as the movement, as well as the land use land cover change. All these things can be observed in various extents using remote sensing and GIS techniques. So why remote sensing has widely been used in degradation studies? It is mainly because of something which is referred as multi-concept, which mainly comprises the following aspects: that remote sensing gives an opportunity to observe a particular region or a particular area using different spectra or different wavelengths. That is nothing but the multispectral observation. Then the second thing is the multi-station. The same area can be observed from different locations or the different angles, ultimately helping in the generation of stereoscopy, as well as the different scale imagery scales can also be obtained. And there is something known as the multi-date or the multi-temporal observation. That means the same area can be observed in different seasons with the same satellite, with the same observation location. So ultimately, these multispectral, multi-station, as well as the multi-temporal observation aspects, they mainly contribute to the object characterization, the identification of various objects as well as processes and their differentiation, and the advantage of the synoptic view and possibility of image enhancement, the information extraction and classification, mainly by using digital processing techniques. So briefly mentioning about the various remote sensing data analysis as well as the interpretation techniques, the most and foremost thing which comes to the mind of a particular person is nothing but the visual or the manual interpretation, where the false color composite will be, people will be trying to analyze the false color composite on the basis of color, tone, texture, pattern, shape, size, etc. for identifying various features. Then is the next one is the digital image processing, where the computer systems, they will be using various algorithms. In that, there are two types of approaches. First one is the image enhancement and the second is the image classification. The image enhancement, it will help to enhance certain features which we are interested in as well as diminish the other things present in the particular scene. Mainly involves the processes such as contrast stretching, the filtering, the spectral indices, the principal components, etc. Coming to the image classification, there are two different ways. The supervised classification, where the user will be determining the majority of the parameters, and the unsupervised, basically it's a clustering or the aggregation mainly based on the spectral similarity. And these are the different algorithms widely used in case of normal multispectral data for supervised as well as the unsupervised classifications. Apart from this, the generation of spectral indices also form a very important aspect in the use of remote sensing and GIS for land degradation studies. These indices, they are mainly derived from the empirical transformations of the various bands using different bands, band ratios, band combinations, normalization and other things. You might have, everyone might have heard about something known as NDVA, that is a normalized difference vegetation index, which we compute mainly using the red as well as the infrared reflectance of a particular feature. Similarly, n number of other indices are also developed based on the requirement people will be choosing. And briefly describing about the basis of visual interpretation, I hope everyone might have seen this n number of times. So the visual interpretation, this is the most commonly used technique for mapping and analysis. The features are mainly distinguished by their characteristic inherent properties or patterns, which are familiar on the image. It is mainly based on the image elements or the elements of image interpretation, which are listed here like tone, location, association, resolution, and many so on. So these are the different standard reflectance, spectral reflectance curves of different features like healthy vegetation, dry soil, wet soil, water, clear water, turbid water, and other things. And these are the reasons why the different characteristic peaks or the absorption plateaus, they are seen. In case of the visible region, the vegetation, they have reflectance peak at green wavelength as well as the absorption peaks at the blue and green, mainly because of the chlorophyll and other pigments. Whereas the NIR plateau or this increased higher reflectance is mainly because of the cell structure as well as the various water absorption bands. So this is the crux of the different spectral reflectance curves. The vegetation reflect up to 50%, soils mainly up to 30 to 40, while the water reflect at most of the 10% of the incoming radiation. So these are the reasons why the different characteristic features occur in visible, the near NIR, mid IR, as well as the change in the reflectance of a particular crop with their crop growth cycle. because the green vegetation becomes yellow or red mainly because of the high reflection in mid IR and low in the NIR, mainly because of the changes in the cell structure as well as the composition of the various pigments. Similarly, the bare soil, it mainly depends on the soil color, moisture content, the presence or absence of carbonates, iron oxides, etc. And similarly, with respect to water, it reflects the electromagnetic energy in the visible up to NIR to up to a certain extent. Beyond 1.2 micrometer, entire amount of energy is absorbed. Whereas if the water is turbid, then there may be containing good amount of sediments as well as chlorophyll. They may have slightly higher reflectance compared to the clear water. So there are certain facts which the interpreter or the person who is going to interpret the particular area needs to keep in mind while before starting the interpretation. First one is the study area. The nature of the vegetation or the other features likely to occur in that area, the person should be somewhat aware about those things. The spatial resolution, that means what is the pixel size of the spatial resolution and what is the season of the satellite data you are going to choose, because the phenological status of the vegetation changes, as well as the physiography. Then there are classification schemes. They are mainly objective and they are mainly controlled by the mapping scale. If it is a very fine resolution scale, there will be more and more detailed classification. Otherwise, if it is a very coarse mapping scale, it will be normal classification on the periphery, like the classification into forest, agriculture, scrub and other things. But when we go into detailed mapping within the forest itself, the type of forest, the type of different season of different crop cycle, all those things will be mapped. So in this, both the resolutions, that is the spatial as well as the spectral resolution, they play a very important role in discriminating the features on the earth as well as, and they are very significant. This is a methodology which is widely, this is a very generalized methodology for the soil as well as land degradation studies adopted at the national level also. So we require at least 2 seasons data. We will be fixing the scale of the mapping. Which data we want to use, that will be decided mainly based on the scale of the mapping. The 2 remote sensing data, they will be undergoing a preliminary visual interpretation, and they will be combined with the information obtained from various ancillary data like the Survey of India topo maps, the climatic data, as well as the public literature, to identify the different types or the nature of land degradation we are expecting in a particular area. And wherever there are confusions or we want to be 100% sure, we will be going for some amount of ground truth collection, where we will be conducting soil profile study or the collection of soil samples from surface or the subsurface layers. They will be analyzed mainly for the chemical degradation like the pH, electrical conductivity, exchangeable sodium percentage. These properties, they will be identified and ultimately assigned for the finalization of the thematic map. And finally, you will be getting a soil or land degradation map with the updation of various land degradation types as well as their severity. So this is the classification scheme of the first land degradation mapping, which was national wasteland mapping using list 3 data initiated in 2006. Now the three cycles have been completed. The data, the outputs for the entire country as well as the different states, this can be obtained or they can be visualized mainly in case of the Bhuvan portal of ISRO. So these are the mainly the major criteria of land degradation they have identified using the 2 season, at least 2 season, and if it is 3 season data is available, it is very well and good, mainly by the on-screen visual interpretation approach. So this is the desertification or the land degradation status map of the India. Out of the 329 million hectares, total area of around 105 million hectare is under different forms of land degradation, and the total area is 81 under desertification, because there is a slight difference between degradation as well as the desertification. So you can see the different codes from the color itself. You can match what are the different types of degradation categories, it is occurring in which type of land use land cover, as well as what is the degree of degradation, whether it is severe or high, and all those information you can obtain. And this is how the water erosion, it can occur both in case of cold as well as the hot regions, because it is mainly determined by the rainfall as well as the runoff. So you can see how the area, this particular area, this is the field photograph, and how the area will look like in the satellite image. So once we have a mind correlation between how the area looks like and how the signature will appear on the satellite image, you will be able to map. That's why in the initially itself, I just mentioned that the person who is interpreting the land degradation map or for any visual interpretation, he should be somewhat aware about the climatic as well as the soil as well as the topographic features of the particular area in which he is going to prepare the map. Here we can see it is very, it's somewhat flat, but still there are low severity erosion, that is a sheet erosion. Major rill you can see is like in agricultural land. Here you can see there are river-like channels. You can these features, and it is very rough textured. You can see this is the how the area looks like in the field. That means the high severity. That means we are having a large number of deep as well as wide gullies as well as ravines. So the severity levels of water erosion, how it occurs on the satellite images as well as in the field. Then comes the vegetal degradation, how it looks like. It also occurs in both hot as well as cold climate. Is mainly observed as deforestation, the forest blanks, the shifting cultivation. So this is how the vegetal degradation with different severity levels, how they are occurring in AVIF data of around 56 meter spatial resolution, how the area, similar area looks like a field. We have the cold deserts. Then this is how the area is shown in the area on the ground, as well as how the area looks like in the image. It will be showing like ripples. And there are something which is very important, and nowadays increasingly the things which have been observed is nothing but the man-made degradation, mainly because of various anthropogenic activities like the mining, quarrying, the bricklin, development of bricklins, as well as the industrial effluents, as well as the city waste. So you can see the variations, but in order to understand this, you should have some idea about the local area, what is the phenomenon happening in those particular region. Another important land degradation type which can be easily identified using remote sensing data is nothing but the water logging. Basically, the undrained the land parcels, they mainly tend to accumulate the standing water, and the water will be accumulating and will be standing on the land surface for very long duration of the time. Mainly observes in case of the alluvial plains where the oxbow lakes or the low-lying areas and even the regions with the shallow water tables. And the severity of the waterlogging, it is mainly determined mainly based on the period for which the water remains stagnant. It can be seasonal waterlogging, it can be permanent waterlogging, it can be temporal waterlogging also. So if it is, if only one crop is possible, that means rice which favors water logging is cultivated. We can see that, and the rest of the all the other seasons still water is remaining in the particular area. It indicates mainly the very severe water logging. If two crops are possible, we can say that it is moderately temporal, moderately water logging. And if it is only one crop is possible, only if all the three crops are possible, then it can very slightly waterlogged. And the waterlogging, this is the field condition, and this is how the area looks like in the particular image. Because as when we discussed about the spectral reflectance curve, we discussed that spectral reflectance curve of this particular of water, it mainly has a signature where the reflectance is very low, and beyond 1.2 micrometers, it will be 0. That means there will not be any reflectance. That's why all these water logged patches, they mainly have a dark, very dark zonation or very dark coloration. Another important aspect of degradation which can be studied mainly using remote sensing is the salinity or the alkalinity. It is nothing but the presence of excess amount of different types of salts. Depending on the nature of the salt, it may be either salinity or it may be alkalinity. So the remote sensing data could reveal the presence of salinity mainly due to the influence on the spectral reflectance. The salt affected soils, they mainly exhibit a very high reflectance in the visible and near infrared spectrum when compared to the non-saline and cultivated soils or the normal soils, and thus they appear as bright white patches in the color infrared aerial photograph or multispectral false color composites. That means if there is a high concentration of salt in a particular region, those areas will be appearing very whitish in color because of the very high reflectance in the visible and near infrared region. And similarly, it has also been identified by various researchers that the soil reflectance, it mainly increases with the increase in the salt concentration. That means higher the salt concentration in the soil, higher will be its reflectance, and thus making the identification of severely salt affected soils much easier when compared to the lower levels of salinity. This is basically the direct observation of salinity mainly using remote sensing. And there is another aspect of indirect observation of salinity also, mainly by studying the impact of salinity on the vegetation growing in the particular area. The visible reflectance of the leaves of the mainly the plants which are growing in the salt affected soils, they are observed to be very lower compared to the if the same plant is grown in the non-salt affected region before the plant maturation, and the trend reverses immediately after the maturity. And similarly, in the NIR, an inverse relationship observed between reflectance and salinity. That means with increase in salinity, the reflectance will be reduced. So the selection of suitable remote sensing data for studying salinity, it should be taken care of by considering certain important factors such as the season of the data capture, then the sensor characteristics, the spectral indices, as well as the digital interpretation or the classification techniques which we are intending to use in a particular scenario. So here we can see the strongly saline sodic soil, they are having the highest reflectance when we observe the area using a Landsat TM image. This is a strongly saline and this is the normal soil. It is having the lowest amount of reflectance. And these are some of the photographs how the area which are affected by salinization as well as alkalinization. They mainly occur in cultivated lands, especially in case of the irrigated areas. So the salinity, they can be clearly observed in satellite images, while the alkali, if the nature of the salt is alkali, that means the carbonates and bicarbonates of sodium is dominant. It may not be seen very clearly, and it is mostly inferred mainly based on the ground truth data by collecting soil samples and their chemical analysis in the laboratory as well as various published maps. Here you can see the severity of salinity or alkalinity, how they appear on satellite images as well as in the field. These two are the field photographs of salt affected region, mainly from the Indo-Gangetic Plain region near Mathura region of Uttar Pradesh. And similarly, the chemical composition of the salts, that means the mineralogy, it may be the presence of sulfates, chlorides, carbonates, etc. They also determine the presence or absence of absorption bands in the entire electromagnetic spectrum. That's why with change in the composition of the salts, the reflectance pattern also varies. Similarly, the variation in the salt mineralogy, it also affects the surface roughness. How? By producing distinct macromorphological features. You can see in the surface it is very dry and there is a certain crumbling of the surface in the form of peeling off in the form of small patches. So that's why the chlorides, if it is dominant, they may produce a white, smooth, salty crust, whereas the abundance of sodium sulfate, they produce puffy crust, as we can see in this particular image. Similarly, in an earlier study, SELAG, they have identified and described 6 spectral ranges, mainly comprising the visible, NIR, as well as the mid-infrared bands, which are useful in characterizing varying degrees of soil salinity. And this is the how the visual interpretation. This is the false color composite of a particular area where the soil is having a saline sodic characteristic with very severe, and this is how the area looks like in a Google Earth image. Here it is very bright, whereas it is a slightly saline sodic soil. You can see there are in between there are red pixels. That means there are some amount of vegetation occurring in this particular area. These are both from the state of UP. And there is another connection between salt affected soils as well as waterlogged soils. There is a high tendency that both salt affected as well as waterlogged soils may coexist in regions. Wherever there is waterlogged, in due course of time, there is a high chance that the area may get salt accumulation also. Here you can see the different categories of salt affected soil, like the waterlogged soil, the moderately salt affected, as well as the strongly salt affected regions, how it is coexisting and which we can observe in a single scene. Here also you can see this is the how, but it's a very quite old image, but it's a classical image of the waterlogged as well as the salt affected region. Here you can see the salt affected region which is having very bright reflectance, and the same area itself you can see this is a very dark colored area, and this is the corresponding photograph of because of the ponding of the surface water in the low-lying areas. So that's with that we have discussed till now regarding how the visual interpretation and the on-screen digitization using multispectral data can help in the various characterization as well as mapping of salt affected soils as well as various degradation types. There is another type of remote sensing, another category of remote sensing, which is known as the hyperspectral remote sensing, which is widely used for not only for the identification but also for the quantification of various properties. Hyperspectral is nothing but the instead of the 4 or 5 bands in which the entire area will be scanned, the data we will be getting at very minute bands of very narrow contiguous bands of having width of nearly 10 nanometer or 10 to 20 nanometer. So the study was conducted for use of hyperspectral remote sensing derived spectral indices for characterizing salt affected soils. And these are the description of the study area, the climate, which data was used, and what were the pre-processing of the data done before identification. Then the reconnaissance survey was also done for identification of salt affected areas. During the reconnaissance survey, various surface as well as subsurface soil samples also were taken along with their GPS coordinates. After that, a correlation analysis was performed between the mean spectral reflectance value of the soil sampling locations and the corresponding soil salinity parameters in order to identify the soil salinity sensitive bands. And these sensitive bands were identified, and these bands were used for the generation of various spectral indices using the different formula or the different band combinations as it's indicated in this particular table given. So once the spectral indices were generated, once again a correlation analysis was conducted to identify which among these different spectral indices is highly sensitive to variations in soil quality, soil salinity parameters. And the major soil salinity parameters, the others they have reported and measured in the soil samples were the electrical conductivity, the pH, the EC, the exchangeable sodium percentage, as well as the sodium absorption ratio. So the salinity index as well as the brightness index, they were found to have the highest correlation index, and these two bands were also identified using a stepwise discriminant analysis to study the effectiveness of these spectral indices in discriminating different degrees of salinity, not only the salinity, but within the salinity itself, whether it is slightly saline, moderately saline, whether it is severe or very severe salinity. So among these, the salinity index was found to be the most suitable index in characterizing the degree of salinity. So once they identified the most sensitive spectral indices, that is the brightness and salinity, they have generated various regression equations for the prediction of various soil salinity parameters of electrical conductivity, sodium absorption ratio, as well as exchangeable sodium percentage. So as we have the spectral index value for the entire pixels, so once we apply this particular regression equation, the spatial distribution of salinity parameters can be observed. Sorry. So this is the spatial distribution of salinity parameters generated using the salinity index as well as the brightness index. Here you can see within the salinity itself, the normal soil, slightly salt affected, moderately salt affected, as well as the highly salt affected soil, they were delineated mainly based on the EC distribution. You can see the values also, the predicted values also. That means it helps in identification, not only identification, but also the quantification also, the exchangeable sodium percentage map also. And finally, based on the value of electrical conductivity as well as the exchangeable sodium percentage, the different soil salinity classes, they were mapped mainly based on the electrical conductivity as well as the exchangeable sodium percentage values. And initially we discussed something about the digital elevation models, and this is just to show how a digital elevation model which contains in each pixel in comparison to a multispectral image, each pixel will contain a value which mainly indicates the elevation of that particular point with respect to mean sea level or any other base. So how it can be used for various watershed delineation as well as the characterization of various hydrological and soil erosion modeling approaches. This is the elevation of a particular watershed. The elevation within this particular small watershed varies from around 660 meters to 2,500 meters above the mean sea level. So using this digital elevation map, we were able to characterize the slope, the incoming solar radiation, each of this area, how much it is receiving, where is there any difference. There is something known as the aspect, which mainly indicates the direction of the slope, as well as we were able to delineate the watershed, the generation of various stream network, how the water flows in this particular area, as well as the generation of a 3D image. These are all possible mainly because of the use of digital elevation models. And regarding the use of remote sensing and GIS, mainly in case of soil erosion studies, as we have seen earlier, the rill as well as the gully erosion, especially in case of the unvegetated or the sparse vegetated landscape, they can be easily identified using aerospace remote sensing data. Similarly, the remote sensing data, they can effectively provide various temporal as well as spatial information that can be coupled with that can be coupled with soil erosion models. Different types of soil erosion models are there, like empirical, semi-empirical, physical process-based models. So the various inputs which are coupled with a soil erosion model and are derived from remote sensing and GIS, they mainly include the soil map, soil moisture condition, spatial estimation, the vegetation cover as well as the land use, the digital elevation model as well as the sediment transfer. In this image, you can see the multiple degraded lands. You can see the severely eroded, moderately eroded, slightly eroded, and the undulating land. You can see the gully erosion, how the gully is from the Chambal region. You can see the rills, how they used to appear in case of the earlier stage aerospace photographs. And this is the visual interpretation. The images have been taken from the third cycle of the National Land Degradation Mapping using visual interpretation. You can see the same area, how it looked like in 2005-06 as well as how it looked like in 2015-16. You can see there is a very clear increase in the reflectance of this particular region. It is mainly because of the water erosion. And this is how earlier this area people used to cultivate in some seasons, but because of the increase in the water as well as the deposition of sand and other coarse material, the area has now become unsuitable for cultivation. Similarly, the landslide, this area appeared quite normal in 2005-06. Now you can see there is a very increased reflectance in the particular polygon. You can see how the area looked like in 2005-06, how the area looks like in Google image, and this is a field photograph of the same area. It's in Dehradun district. It's in Dehradun district only. Similarly, the landslide, we can see in 5-6 there was nothing, and 15-16 there is a landslide. In between, the landslide has obtained. And then you can see these areas, how the deposition of sand particles has made these areas not at all suitable for any of the agriculture or crop production activities. And coming to the various input maps as well as a soil erosion risk map we can generate using the remote sensing data. We discussed that the land use land cover map can be generated for the particular area. It can be either generated using the on-screen visual interpretation or on-screen digitization, as well as the various supervised and unsupervised classification. So this image we have generated is for a hilly watershed in Uttarakhand. We have generated using on-screen digitization only, where the dense forest, moderate forest, open forest, agriculture, horticulture, agri, different categories of scrub, water body, all these things have been identified. Similarly, a physiographic map has been generated, a soil map, mainly for the soil survey approach, mainly by combining the information we obtain from the landform categories in the area, then the slope characteristics, as well as the land use land cover. By combining these different categories, we can generate various physiographic soil mapping units. We will be conducting soil survey in these different soil mapping units. We will be characterizing the soil and ultimately generating a physiographic soil map. So it will give an idea about the different soil characteristics of the particular area, such as the depth, the coarse fragments, what is the slope, what is the organic matter content, all those things. The spatial estimation can be done, and the physiographic soil map is the basis for undertaking the soil survey. This is the slope map, which can be mainly generated from the DEM. This is the soil erodibility factor map, which is generated using the organic matter content, the textural composition, that is the sand, silt, clay, as well as a structure and permeability code using the physiographic soil map. And this is a slope length steepness factor, which is known as the LS factor, mainly generated using the slope as well as slope length as well as the slope steepness. This crop cover as well as the support practice factor, these are mainly derived using the land use land cover map. So ultimately, combining all these different erosion controlling or erosion determining factors in a geospatial domain, we can generate the soil erosion risk map of the area by using a particular empirical model, which is known as the revised universal soil loss equation, or the Rusley model. This is so we can characterize the different areas. So we can just identify, even if there are minor variations in the absolute value, from the relative identification of areas which are having a high risk of soil erosion, this model works very good for regional planning or the identification or the implementation, planning and implementation of soil as well as water conservation structures. And this is a soil erosion risk assessment done for another watershed, a hilly watershed. You can see the blue color indicates the areas where the risk is only 0 to 10 tons per hectare per year. This area have 10 to 20, and these red colored patches, they are having a soil erosion risk of more than 40 tons per hectare per year. So this type of comparative assessment help us in the planning as well as the adoption of various soil as well as water conservation methods. So till now we have discussed about the watershed level studies, and recently we have done the geospatial modeling of soil erosion as well as the risk assessment in the Indian Himalayan region. The study was done by myself and my colleagues from the department. So we have done extended the by making modifications to the model structure and using various globally available high resolution global data sets for the erosivity, the soil grids, the CARTO-DM as well as the land use land cover. We have employed the revised universal soil loss equation and assessed the spatial distribution of soil erosion risk for the entire state. This is the potential soil erosion risk map. It is the potential. It's not that this will occur, but the chances are high. So this is the potential soil erosion risk map of the entire Uttarakhand state, excluding the snow-covered area. So coming to then further we made a study to assess the mean erosion rate as well as the total soil loss under the different river basins, and we found that the Yamuna basin was found to have the highest mean erosion rate. And similarly, the total area which comes under the different categories of soil erosion, that means around 20.34% of the total geographical area of the state was found to have a soil erosion risk of more than 40 tons per hectare per year. So, and similarly, the highest and the lowest amount of soil loss, they was estimated to originate from the middle Himalaya as well as the Terai regions, which are the different physiographic units. So this type of soil erosion map, this can serve as a tool for the area prioritization as well as effective planning and implementation of management as well as conservation practices, mainly for controlling the soil erosion. Similarly, now recently people have started using the UAV or the drones also for monitoring soil erosion, normally at the field level or the field scale, because the resolution of the images or the products we generate using the DEM, it mainly helps in reducing the gap between the field scale as well as the satellite scale in erosion modeling. So the ortho image or the mosaics of the study area, they enables or helps in the creation of digital terrain models as well as the ortho image mosaics with very high resolution to the tune of 10 centimeter, 20 centimeter accuracy. This is the ortho image, this is the ortho photograph of the particular gully. This is a gully structure, and this is the generated digital terrain model of the study area. So using this digital terrain model, they found that the maximum incision depth or the depth of this gully, it reaches around 4.25 meter from the surface at the lowest point, that is somewhere around the outlet, and it gradually decreases when we move up the gully towards the more recently eroded areas. Similarly, it can also help us in estimating the gully volume change. How? We can generate a DEM of this particular area before the rainy season, and after 1 year or immediately after the rainy season also, you can generate the same DEM of the same area at the same flying height. So you will be getting 2 DEMs of the same area, then at the 2 different time periods. So both the negative, that means the erosion, if the depth is increasing or the change is negative, that means more erosion has happened. And positive means the depth has decreased. That means infilling due to dam leveling and other changes. So such type of generated DEMs, they could be used for detailed hydrological as well as the terrain modeling. And this is how the ravinous lands along the Chambal River it occur. So these bright red patches, these are nothing but the good agricultural areas or the cropped areas, where these these are mainly highly dissected ravinous lands, where immediately after the rainy season we will have good amount of lush vegetative growth from the scrubs and other things. But once the moisture availability gets decreased, this entire area becomes dried. Because of the land dissection only, the entire area appears very rough in texture. And people have used other techniques like the SAR interferometry also has been used by some people for the identification of the ravines, the estimation of the ravine density as well as the spatial disposition. Similarly, another application, this is using a hyperspectral remote sensing data. A case study was conducted for identification of different soil types. That means a person who has worked in remote sensing, they might be knowing that there are different types of soil like red soil, green soil, something the different based on the colors. The properties also vary based on the different colors. So these things which appear as these greenish tinge, they are nothing but the red soil areas, and these dark patches, they are nothing but the black soil within the same vicinity. So this area was classified using a SAM classifier, using another classifier of SVM data, using reflectance as well as an SVM using an MNF component. These are some of the technical terms which are mainly involved in the generation or the production of hyperspectral image during the image processing. So they found that we could find that the use of the MNF components, they altogether improvised the soil classification. So the overall classification accuracy was 86%, whereas the red soil we were able to classify with a percentage of 91% accuracy, whereas the black soil, which was around 78%. Similarly, another important aspect of remote sensing or the GIS or the geospatial technology with respect to agriculture and soils is nothing but the soil moisture content estimation. I'm not going into the detail of all these things. The estimation of soil moisture content, it is a very important aspect of precision irrigation, water management, or the regional planning related to the crop yield production, crop yield modeling, and other things. So people have used both thermal as well as the microwave remote sensing data. They have been widely known to show significant results in the mapping the variation in moisture levels, especially in case of scattered crop areas. So there are n number of literature available related to soil moisture estimation using microwave as well as the thermal data. So if someone is interested, you may go through all these things. It's available in open domain also. Apart from this, nowadays recently another concept has gained the attention of various people working in soil survey as well as the soil mapping. That is nothing but the digital soil mapping. So we undertook a case study. We undertook an attempt to see the possibility of using remote sensing as well as geospatial technology, mainly for the digital soil mapping conducted in a Himalayan watershed for using an artificial neural network model. It's a machine learning or artificial intelligence model. The study was conducted in a hilly watershed in the Himalayan region. We generated the spectral indices like the coloration, brightness, hue, redness as using the Landsat 8 satellite data, and derived certain terrain parameters using digital terrain analysis like the terrain wetness index, the stream power index, as well as the slope using a Kato 30-meter DE. So the predictive modeling of carbon we have attempted using a CNN network, and we were able to predict soil organic carbon for the entire study area with an R-square value of 0.83 and a mean square value of 0.05. So this is the spatial distribution map of the soil organic carbon we were able to generate. Similarly, the hyperspectral modeling was also attempted for mapping of soil properties. It's also widely used using a sensor known as an airborne sensor. It is the IIRS NG. So the spatial prediction and mapping of soil property was undertaken mainly using a chemometric technique, which is known as the partial least square regression modeling. So these are the study area details as well as the methodology adopted. So the PLSR based modeling, it helps in the selection of optimal wavelengths among the around 200 to 400 wavelengths which are we obtain the value from. We can choose the optimal wavelengths which are sensitive to various soil properties. And these selected wavelengths will be used for the predictive models. And these validated models, they are widely used for the mapping of soil organic carbon, nitrogen, as well as the clay content. Here only the colored pixels, because this model we could apply only onto the bare soil surface. So wherever the pixels had a good amount of vegetation, we have masked those areas, and the model was applied only onto the masked soil pixels only. Similarly, people have also made attempt for the, identification of different types of soil clay minerals using hyperspectral analysis. The study area details and the various methodology, it's also given here. The absorption features in the spectra. These are the things which are known as the absorption features, mainly because of the variations in the chemical composition, mainly by the overtones as well as the fundamental absorption bands. So they were characterizing the shape as well as the wavelength position of the strongest absorption features. They were characterized. And the absorption feature parameters, what is the depth of this, what is the width, what is the area, what is the symmetry, and all other things, they were estimated. And this is the original as well as the continuum removed spectra for a kaolinite. There is a 1:1 type of clay mineral dominant soil sample. So this is the concept of continuum and how the continuum removal is there. And similarly, for some of the samples of the area, the dominant clay minerals in those samples, they were predicted using the absorption feature parameters as input parameters, employing a random forest model. And they were also identified using an XRD for verification to identify how much accurately we were able to identify the soil minerals. So among the different absorption depth parameters, the width of the absorption was found to be the most important variable for prediction, which explains around 31% of the variance. And the unknown samples, they were able to classify with an accuracy of 0.7. And this is the error matrix of the random forest based classification. And using this concept and extrapolating onto a spatial domain, the Hyperion data of the area was classified using a SAM algorithm. The algorithm was trained based on the field observations in combination with XRD analysis, and the cavolite was found to be the most dominant mineral, followed by the montmorillonite in the entire area. You can see this is the cavolite, the goethite, the montmorillonite, illite, as well as the vermiculite. These are the different types of soil clay minerals belonging to 1:1 as well as the 2:1 type of clay minerals. And the overall accuracy of the classification was found to be around 68%. The study area, the uplands are mainly with non-expanding clay minerals, while the lowlands or the bottom portion of the image, they are mainly dominated by expanding clay minerals. Similarly, for the mapping, a spatial mapping of soil organic carbon, it can also be predicted using the various remote sensing data. The study was conducted in a part of the Narmada River basin. The detailed field survey was conducted to estimate the soil organic carbon stock. Around 210 soil samples were collected. And remote sensing derived different predictor variables were generated, like the brightness index, the greenness, wetness, NDVI, VTCI, elevation, slope, as well as a compound topographic index. And a regression kriging approach was used using these various remote sensing based inputs. And these are the overall methodology used. You can see the spatial distribution of soil organic carbon they were able to identify. And you can see the range of the soil organic carbon stock in the particular area. It varied from 0.28 to 31.95 gram per kilogram in the study area. And these are the model performance characteristics like calibration, validation, RMSE, and other things. Similarly, nowadays, the precision agriculture, many people might have been increasingly hearing about the precision agriculture. In precision agriculture also, the geospatial technology plays a very important role. You might have heard about the GPS mounted combine harvester. So each and every location, the yield will be noted along with the GPS location. So ultimately, such type of information or the geo-referenced yield observations, it will ultimately help in generation of yield maps within smaller areas, such as in case of a field. Here you can see that this area or the green patches, they are having a higher yield of 10 tons per hectare, whereas these areas near these boundaries, they are having a lower yield. So if you want to adopt a variable dry technology like adjusting the fertilizer recommendation or the crop protection or the irrigation management, we need to put our focus on these areas where the yield map shows very low values to the tune of 1 or 2 tons per hectare. So it will help in the generation of spatial yield variability within field as well as the farm. It will ultimately helps in the decision making with respect to the variable rate technology as well as many other applications for irrigation scheduling, fertilization, and you can skip the fertilizer for 1 or 2 years in certain areas where we have very higher amount of yield. So it depends on the application which you are interested in. So this is the wheat grain yield map of the study area. They are mainly overlaid with the village boundaries. So within a particular locality, which village is having higher fertility or higher yield, or we can in depth, we can go for the study of how this particular area and what may be the reason for the higher or the improved yield in this particular area. All these things can be identified. Another important aspect in which remote sensing as well as the various geospatial technology has been widely used in agriculture as well as the soil studies is the land evaluation, which is widely used as a tool for strategic land use planning. So land evaluation is nothing but assessing the land performance and its production potential for a specific purpose, whether that particular land is suitable for a particular crop or not. Even if it is suitable, up to what extent it is suitable, whether it is highly suitable, moderately suitable, such type of comparisons we can do for a spatial area. It is basically a part of the process which is known as the land use planning. So once we have a data regarding the characteristics of the land as well as its production potential, we can allocate the land parcels into different uses. That is known as the land use planning. So the function of land use planning is to guide the decisions on land use in such a way that the various resources of the environment, they are put to the most sustainable use for us, while at the same time conserving those resources for the coming generations or the future. So the land evaluation, they mainly answer the following questions: how the land is currently managed and what will happen if present practices remain unchanged. Second is what improvements in the management practices within the present use are possible, what are the possibilities, and what other uses of land they are physically possible and economically as well as socially relevant, so that the people in that particular area adopt those particular suggestions or the improvements. and which of these uses offer the possibilities of sustained production or other benefits, as well as what adverse effects, physical, economic, or social, they are associated with each use. The evaluation process, it does not determine the land use change, but it provides the data based on which the decision maker, including us or you, can take decisions to identify that whether a particular land is fit for what purpose, whether this particular land is fit for agriculture or it is fit for forestry, or even if it is suitable for agriculture, it is suitable for which type of crop, depending on the various land as well as the climatic parameters. Coming to a particular study reported from the Mysore district of Karnataka, the authors, they have studied, they have tried to assess the land suitability mainly for the maize crop in a semi-arid ecosystem of southern India using an integrated AHP as well as a GIS approach. AHP is nothing but a multi-criteria decision-making analysis tool, mainly widely used. So in this, the satellite data, mainly the digital elevation model was used mainly for the generation of elevation. Then the observatory data, they have collected certain climatological data like the rainfall as well as the potential evapotranspiration. Then they have computed the soil storage and the computation of the length of growing period. Then they have conducted a detailed soil survey by the visual interpretation of multispectral data for identifying the various soil sampling units, and they have generated the database comprising of the details of various locations of the different sampling units in the area with respect to slope, depth, texture, drainage, organic carbon, as well as pH. Then all these different factors, they were undergone through a pairwise comparison for the identifying the differences in their weightages, because certain parameters will be more important for a particular crop in comparison to others. So it's basically the pairwise comparison. Ultimately, it gave the weights. These weights were used for the weighted overlay of these different parametric layers in the GIS. Ultimately, the land suitability for maize was computed and it was reclassified for the generation of the final suitability map of the particular area. And ultimately, a comparative analysis of the suitability classes with the how much amount of area is actually grown under maize, that was also done by the authors. So this is the criteria, this is the main criteria and this is the sub criteria. Within the elevation itself, the different classes were defined for the different types of suitability like slope, LGP, soil depth, soil texture, drainage, etc. These are the different input maps which are generated using the geospatial technology, using ground validated, ground collected information, as well as the remote sensing input data. All these parameters, these listed parameters, they were subjected to a pairwise matrix comparison using an AHP analysis, and the weightages of all these different parameters, you can see among these the highest weightage is with respect to depth. Yeah, it is depth, then the length of growing period. So from this we can understand that all the different parameters are not equally important for deciding the suitability of a particular tract or a particular area for suitability of particular crop. Here in this case, it is maize. So based on the weighted overlay of this particular area, this is the suitability map of the entire district after deduction of the forest as well as the these areas, so the settlement areas. So here you can see the green color indicates the areas which are highly suitable, and this indicates the areas which are moderately suitable, and this is the area which indicates the marginally suitable, and there are certain areas which are not at all suitable for cultivation of maize. So this is the area statistics after the deduction of the miscellaneous classes. So out of the total area, around 29% is highly suitable, and 18% is marginally suitable, and 15% is moderately suitable, whereas out of the total area, only 9.5% area is not at all suitable for maize cultivation. Then further, they have compared with the statistics from the different taluka level, the total geographical area, what is the percentage area they have cultivated and what is the gap, and they found how much amount of, this is the total geographical area of maize at the different tehsil level. You can see that on an average around 38.4% is the gap between the area which is originally suitable for maize cultivation and the area which is originally cultivated right now. So this can be an important information for the various planners as well as the decision making if they want to improve or enhance the amount of area which is cultivated under particular crop. Here in this case, it is maize. So people may take various actions for increasing the area which is cultivated under maize, or we can try to identify what are the reasons which are stopping the people from cultivating a particular crop in this particular region. Similarly, for hilly and other regions, there is an FAO approach mainly for land capability classification, especially with respect to the hilly watersheds. So hilly watersheds, there have been the attempt has only been mainly based on the slope as well as the depth. The combination of the slope as well as the soil depth, they mainly determines the suitability of the particular piece of land in this hilly terrains for different types of applications. So if the slope is less than 7 degree and the depth is more than 90, it is comes under the category C1, that is, it is a cultivable land with only very slight limitation with respect to these factors. Whereas there are combination of very strongly slope, that is 20 to 25 degree slope, and there is a shallow depth of 20 to 50 centimeter. You can see this area is suitable mainly for pasture. Similarly, the F is mainly for the areas which are suitable for forest, as well as there are areas which are suitable for fruit trees, mainly depending on the characteristics of slope as well as the depth of the particular hilly region. So this is how, from a digital elevation model, we can generate the slope. From the physiographic soil map, you can generate the soil depth. By integrating them in a geospatial environment, we can generate the land capability map. So this is the slope map of a particular watershed, and this is the soil depth of a particular watershed. When we cross both these things, the combination of slope as well as the depth ultimately gives a land capability classification for this particular area, where the different areas suitable for various purposes can be identified. That is the cultivable land 1, C1, it is basically the where we can go for the intensive cultivation of various crops along with the adoption of various agronomic measures. Then the cultivatable 2, we can go for agronomic measures. In case of the cultivable land 3, that is a C3 and C4, we should go for agro-horticulture by combining seasonal as well as the perennial crops. Then cultivable 3 as well as pasture, we should adopt agro-horticulture as well as the agroforestry practices. And there are certain areas which should be left as such for the forest development of forest as well as the scrubs and other natural vegetation in the particular region. So this is in short regarding the various applications of remote sensing and GIS, especially with respect to soil related studies or soil related applications. So that's it from my side. And if you have any queries, I will be happy to answer them.